Hello guys, we want to start our 7th lecture on transform calculus and partial differential equation. In this lecture, I want to talk about partial fraction, and then we want to see how we can use partial fraction to find Laplace inverse of different functions. If you remember, in the last lecture, we solved one example. So the example that we solved, we said if you want to find Laplace inverse of 3s plus 11 over s squared minus s minus 6. So we saw that this fraction 3s plus 11 over s squared minus s minus 6 is not similar to the functions that we already found the Laplace transform. So we cannot find something similar in the table of Laplace transform. As a result, we said if you want to solve it, we have to decompose it. So at first we factored denominator, so we had s minus 3 times s plus 2. So numerator is the same. And then we found its partial fraction. So we said it's equal to Laplace inverse of 4 divided by s minus 3 minus 1 over s plus 2. Now we can easily find Laplace inverse of this function. So the process of taking a rational expression and decomposing it into simpler rational expressions that we can add or subtract to get the original rational expression is called partial fraction decomposition. For example, for our example, so we had one rational expression. So the rational expression that we had was 3s plus 11 divided by s squared minus s minus 6. And then we decompose it into simple or simpler rational expressions. So the rational expressions that we found was 4 over s minus 3 and 1 over s plus 2. And we could add or subtract them to get the original rational expression. So this process is called partial fraction decomposition. But the question is how we can find partial fractions of the original or the original function that we have. So let's assume we have fs is equal to ps over qs. So ps and qs are polynomials and degree of ps is smaller than that of qs. So imagine in this case, so we have fs in our example is equal to 3s plus 11 divided by s squared minus s minus 6. So it's equal to ps over qs. So in fact, ps in our example is equal to 3s plus 11. qs is equal to s squared minus s minus 6. So degree of polynomial in numerator should be less than degree of polynomial in denominator. So what's the degree of polynomial? Degree of a polynomial is the largest exponent in the polynomial. For example, here the largest exponent is s to the power of 1. As a result, degree of polynomial ps is 1. The largest exponent in qs is 2. You have s to the power of 2. As a result, degree of qs is 2. So degree of numerator for sure should be less than degree of denominator if you want to use partial fraction. For partial fraction decomposition, we factor the denominator as completely as possible. Then for each factor in denominator, we use following table to determine the terms we pick up in the partial fraction decomposition. see, we have to use this table. So for partial fraction decomposition, at first we have to factor denominator. So we have our function, which is 3s plus 11 divided by s squared minus s minus 6. So first of all, we have to factor denominator as completely as possible. So we have s minus 3 times s plus 2. Numerator is the same. Then for each factor in denominator, we have to look at this table to find partial fractions, the terms in partial fraction decomposition. For example, at first I look at s minus 3. So here in this table, in the left column, it says that if your factor in denominator is as plus b, a and b, they are constant, then term in partial fraction decomposition should be a capital, which is unknown, divided by as plus b. So when we have s minus 3 here, we have s minus 3 here. In fact, we are in the first category because a is equal to 1, b is minus 3. As a result, we have s minus 3. So the term in partial fraction should be a capital divided by s minus 3. So for the second term, we have s plus 2. Again, we are in the first category. So in this case, a is equal to 1 and b is equal to 2. As a result, term used in partial fraction is again a divided by as plus b. But you know, since we already used a capital, now I use another letter, so which is unknown as well. So it's divided by s plus 2. So a over s minus 3 and b over s plus 2. So they are partial fractions of our original function, which is 3s plus 11 over s squared minus s minus 6. Now what we have to do, we have to find a capital, which is unknown, and then we have to find b capital, which is unknown as well. So for finding a capital and b capital, we have two different solutions. In the next example, we're gonna see what the solutions are. So we want to solve this example. So we already solved it. So it's 3s plus 11 over s squared minus s minus 6. We said we have to use Laplace. We have to use partial fraction decomposition if you want to solve this Laplace inverse. So Laplace, you want to find Laplace inverse of 3s plus 11 over s squared minus s minus 6. So we want to use partial fraction decomposition. So we said first step in solving the problem. So we have to factor denominator as completely as possible. So how we can factor denominators? We have s squared minus s minus 6. You remember that for finding for finding the roots of s squared minus s minus 6 or factoring this, so you know in the past we had, if we have s plus a times s plus b, and if I expand it, it's equal to s squared plus a plus b times s plus a b. Okay. So now we have s squared. Here we have s squared. You know we have to find a and b. Summation of a and b in our example is minus 1, and product of a and b is minus 6. So you have to find two a and b's that if you multiply, you end up with minus 6, and if you add them together, you end up with minus 1. So for sure S should be, A should be minus 3 and B should be plus 2. Plus 2 times minus 3 is minus 6, so we have minus 6. Plus 2 minus 3 is minus 1, so we have minus 1. So as a result, we could factor this function. If you want to factor this function, you have another solution as well. So you know that if you have a general polynomial, the second order polynomial like as squared plus bs plus c, and you want to find roots of these polynomials, so we have s minus x1 times s minus x2. For finding x1 and x2, we can say it's equal to minus b plus minus root b squared minus 4 times a times c divided by 2a. So for this example, so if you want to find x1 and x2, so we have minus b. Minus b in our example is minus 1 and is minus 1. So as a result, minus times minus 1 is plus 1 plus minus root b squared is 1 minus 4 times a here is 1 times c in our example is minus 6. Divided by 2. As a result, x1 is equal to, here we have 1 plus 24 is 25, root of 25 is 5, so 1 plus 5 divided by 2 is 6 divided by 2 is 3, and x2 is 1 minus 5 divided by 2 is minus 4 divided by 2 is minus 2. So for our example, s squared minus s minus 6, we have s minus x1 is 3 and x2 is minus 2. Minus times minus is plus 2. So we could end up with the same result that we have. So the first step in partial fraction decomposition is to decompose fraction as much as possible. So second step, we have to look at the table. Second step in the solution, so we have to pick up partial fraction terms. From table. So in fact, the original function was 3s plus 11 over s squared minus s minus 6. Then we factored denominator. We had s minus 3 times s plus 2. Numerator is the same. Now we have two factors in denominator, s minus 3, s plus 2. So we have to look at the table for s minus 3. If we see the table, so if we have as plus b, so we are in the first category. So the term in partial fraction is a capital over as plus b. So the term in partial fraction for s minus 3 is a capital divided by s minus 3 plus. For the other factor in denominator, so we have s plus 2. If we look at the table, again, we are in the first category. In this case, a is 1, b is 2. As a result, I have to use this term in partial fraction decomposition. So since I already used a capital as one unknown, now I use b capital, s plus 2. So now we know the partial fraction terms. What we have to do, we have to find A and B. I mean A capital and B capital. So in order to find A and B, I just add these two terms. So we have S minus 3 times S plus 2. So here A capital should be multiplied by S plus 2, and B should be multiplied by S minus 3. So now we have two fractions. They are equal. 3s plus 11 over s minus 3 times s plus 2. It's equal to A capital S plus 2 plus B capital S minus 3 divided by S minus 3 times S plus 2. So we have two fractions, they are equal, denominator is the same. As a result, numerator should be the same. So we can say that 3s plus 11 should be equal to A capital times S plus 2 plus B capital times S minus 3. So in order to find A capital and B capital from this equation, we have two solutions. The first solution is a general solution and it works for all the problems. So what we have to do, we say 3s plus 11 left hand side of equation, and then I expand the right hand side of the equation is equal to A times S plus 2 times A plus B times S minus 3 times B, and then I factor S. We have A capital AS plus BS plus B, and the rest is 2A minus 3B. So now you just compare left hand side of equation and right hand side of equation. Here we have 3s plus 11. Here in the right hand side we have A plus B times S plus 2A minus 3B. If you want to have these two equations, these two polynomials equal, A plus B should be equal to 3. And 2A minus 3B should be equal to 11. 2A minus 3B should be equal to 11. So now we have two equations, two unknowns. We can easily find A and B. So I just multiply the first equation by minus 2. So it's minus 2A minus 2B is equal to minus 6. The second one we have 2A minus 3B is equal to 11. Now I add them together. So minus 2A plus 2A gone. So we have minus 5B. It's equal to 5. So it's minus 5B is equal to 5. As a result, B is equal to minus 1. And we have A plus B is equal to 3. B is minus 1. So A should be equal to 4. So we could find A and B. In fact, now we can say that 3s plus 11 divided by s minus 3 times s plus 2, it's equal to we had A here, we had A over s minus 3, so A we found it is 4, so as a result we have 4 divided by s minus 3, and B is minus 1, so we had B over s plus 2, So we have minus 1 over s plus 2. So we could find coefficients a and b, and we could find partial fractions of our original function, which was 3s plus 11 over s minus 3 plus 2. It was the first solution. The first solution is a general solution, and it always works. So the first solution always works. It means that you can apply it to all the problems and you can end up with the solution. We can end up with the partial fractions. But we have another solution. So second solution. In the second solution, so here you had here, see this equation, you had 3s plus 11 is equal to a times s plus 2 plus b times s minus 3. In this case, we don't expand right hand side of equation. We just write 3s plus 11 it's equal to a times s plus 2 plus b times s minus 3. So we want to find a and b, but we don't want to expand right hand side of the equation. So we have two equations, they are equal. If they are equal, it means that they are equal for all the values of s. As a result, if I plug 2s in the equation, for sure it should work. For the first one, I assume that s is equal to minus 2. S is equal to minus 2. What's left hand side of the equation? We have 3 times minus 2 is minus 6 plus 11 is 5. It's equal to. So right hand side of the equation, we have minus 2 plus 2 is 0. 0 times a is 0. As a result, a is gone. The only thing left is b. So we have b times s minus 3. S is minus 2 minus 2 minus 3 is minus 5. So it's equal to minus 5b. As a result, b is equal to minus 1. So you can see that it's very, very easier and faster. For finding a, so I have to get rid of b. As a result, I plug s equal to 3 in the equation. So I assume that s is equal to 3. As a result, right hand side of equation, left hand side of equation, we have 3 times 3 is 9. 9 plus 11 is 20. It's equal to, so right hand side of the equation, 3 plus 2 is 5, so it's 5a. Plus 3 minus 3 is 0. 0 times b is 0. As a result, we can easily find a equal to 4. So we could end up with the same a and b. So in the past, using the first solution here, we found b is equal to minus 1 and a is equal to 4. Here we found the same result. But this solution sometimes works. So second solution, sometimes work. What does it mean? It means that for some problems you cannot apply second solution. If you apply the second solution, you will not end up with the result. But if you apply second solution in one problem and you get the unknown coefficient, for sure your solution is correct. But for some problems, it's not doable to use second solution. So in the next example, we can see when it's not practical to use second solution. So let's back to our example. So we wanted to find Laplace inverse of 3s plus 11 over s squared minus s minus 6. So we said using partial fraction, it's equal to 4 over s minus 3 minus 1 over s plus 2. And so we know that Laplace transform of 4 over s minus 3 is equal to 4e to the power of 3t minus Laplace inverse of 1 over s plus 2 is e to the power of minus 2t. So we could end up with the solution.